Unit 8.1 Waves and Sound by Chris, Nick, and Clint. One of the main equations you'll be using in this unit is V equals F times wavelength, where V equals the velocity of the waves, or the speed of the waves, in meters per second. F equals the frequency in hertz, and lambda equals the wavelength in meters. The types of waves. Transversal waves are waves where their displacement is perpendicular to their motion. So, to explain it better, you can see that the amplitude, or where the waves are changing, is perpendicular to the motion where this wave would be moving to the right. The wavelength is also from crest to crest of the wave. For longitudinal waves, their displacement is in the same direction as their movement. So if you think of it like a slinky, it can still move left to right, and it also can compress left to right. An example of a transversal wave is if you just have a string and you wiggle it, it will create waves that have amplitude and you'll be able to see them. And then in longitudinal, those are just sound waves that move through the air. Standing waves. Standing waves are just two waves that interfere with each other in such a way where nodes are created and antinodes are created. Nodes are created where there's exactly zero amplitude, and antinodes are created where it's max amplitude of the wave. The distance between nodes is wavelength divided by 2, or you can say that wavelength is equal to the distance between nodes times 2. Interference. There's two types of interference. Constructive interference is when two waves are said to be in phase, or where they line up, and so when they meet, they create bigger amplitudes of the wave. In destructive interference, the waves are said to be out of phase, to where the waves don't line up, where their amplitudes are opposite of each other, and so then it creates no waves, or they destruct each other. The natural frequency is at the frequency in which an object tends to vibrate. So this is why we see wine glasses often break when people sing, because you can sing at the wine glass's natural frequency pretty easily, and since wine glasses are so thin and they have a really high tendency to resonate, they will break.
If you sing the natural frequency of the can, it'll explode.
So for harmonics, when a standing wave goes through an open tube at both ends, the length will be wavelength divided by 2. In the second harmonic, the length will be wavelength, and the third harmonic, the length will be 3 times wavelength divided by 2. And we can see that that goes up by 1/2 every single time you move up a harmonic. For a closed tube, is length equals wavelength divided by 4. In the third harmonic, we see that length is equal to 3 times wavelength divided by 4. In the fifth harmonic, we get length is equal to 5 times wavelength divided by 4. And it will keep moving up like that. So for the Doppler effect, we have an equation where the final frequency is equal to the velocity of waves plus or minus the velocity of an observer divided by the velocity of the waves plus or minus the velocity of the sound source times the initial frequency. For beat frequency is when what sound approaches your ear constructively and deconstructively alternating. So it sounds like there's a slight beat in the sound. This can be represented by the equation the frequency of the beat is equal to F1 minus F2, where F1 is one of the sound's frequencies and F2 is the other sound's frequency. Okay, so now we have a simple free response problem regarding waves. The first question asks, why is the tension at point P greater than the tension at point Q? And so, as seen by the picture, we can tell that there's more mass of the rope below point P than there is below point Q. So if we were to do the force of tension equals mass times gravity, and gravity is a constant, the only factor that plays into our force of tension is the mass. And so, because the mass of point P, or below point P, is greater, we know that the force of tension of point P is going to be greater than the force of tension below Q. Okay, so now for the second question, it asks, increasing tension in a rope increases the speed. So we need to explain that. And so the first thing you'd want to do is note that the wavelength of point P is greater, or is just greater, not equal sign, is greater than the wavelength at point Q. And so we'd want to make a note of that in our essay, that the wavelength of point P, is greater than the wavelength of Q. And so then the next thing we want to note is that the tension below point P is greater than the tension below point Q. So then the force of tension is greater at point P than the force of tension at point Q. And then the next thing we want to note is that the frequency is determined by the oscillator up here. So frequency has no effect on our speed because it's constant. And we would know that because V equals F times wavelength. And if F is constant, it will have no factor playing into our speed. And so now we can say that the wavelength is the only thing that plays a factor into how fast our rope is moving. And so, or how fast the waves travel along the rope. And so now we can conclude that because the wavelength at point P is longer and it has a higher tension, we can say that the tension in the rope creates longer wavelengths, which creates a higher speed. Okay, so now we have a second free response question. The question says that 4 strings are attached to oscillators on a table, while the other end of the string is attached to a block that hangs off the end of the table. The question also says that the length of all the strings are the same, and the mass of the block that is attached to the strings are all the same. It also says that the fundamental frequencies of all the strings are different. And so the first question asks, why are the fundamental frequencies of all these different? So we know by the first harmonic that length equals wavelength divided by 2. So that means that wavelength equals 2L. And since L is the same for all of the strings, we know that wavelength is the same for all the strings. And so when we use the equation V equals frequency times wavelength, and wavelength is a constant, the only other variable that could affect the fundamental frequency is the velocity. So we would say velocity is the answer for this question. The next question states that a student graphs frequency as a function of the inverse of the linear mass density. The linear mass density, by the way, is the m divided by L part in the equation. Will the graph be linear? And explain your answer. So first we know that V equals F times wavelength as stated earlier, and we also know that in this case V equals the square root of Ft divided by the linear mass density in a square root. And so then we can say by that the first equation, F times wavelength, equals the square root of Ft divided by the linear mass density. And so when we solve for wavelength, we get F equals the square root of Ft divided by wavelength times 1 over the square root of the linear mass density. And so we know that when we put this into a y equals mx plus b form, the y would be frequency, m would be the square root of Ft divided by wavelength, and the x would be 1 divided by the square root of the linear mass density. And so we know that 1 divided by the square root of something in a function will definitely not be a linear graph. And so that's how we say that the graph is not linear.